writing code, it's coming up with so many projects. So at the top here we have start projects, and these are to do things right or do them fast. If you do them fast, you can code fast, you keep on going around the little loop until it works. Does it work yet? Almost, but it's become a massive collages and spaghetti code. Throw it all out and start over again. So you decide to do it right the next time. You code it well. Are you done yet? You keep on going around until it's done. You've got some great code. And by this time, the requirements have changed. When you go into your careers, you might find this happens quite a bit. It certainly happens a lot in academia when software is developed. Research goals change, they get amended, they evolve over time. You have codes that you've written to accomplish a certain set of goals, and the requirements change, and you need to start thinking about how to extend it, etc., so on and so forth. And then what happens is, oh dear, we've come to the end of the project, it's not quite right, we'll start it all over again in the next project, see if we can get it right the next time. And then of course down here, good code. How do you get to that? Interesting question. So what are we going to do today? So what we're going to do in this lecture is we're going to have a look at another field of science, medical science. We're going to see a little bit about how the history of medical science actually came about, how that's applied. Quick look at that. We're also going to have a very quick look at computer science and how that relates to actually developing software in the real world. A little bit about that. And then we're actually going to go on to talk about some of the things we actually know about software development that's been studied and researched. And then at 12, what I'm going to do is I'm going to set an exercise for you. And at 12, or any other time that you wish, there's going to be a little exercise for you to do in your groups or on your own, where you think about what actually makes code good. And this should start the discussions between you and your group about what kinds of practices you bring into your group project. And then at 2 o'clock, start, we'll come back and bring it all together and see what we've done. So a little bit of a history lesson. So there was this thing called the 7 Years' War, 1754 to 1763. Okay. Britain loses over 1,500 sailors to enemy action. 100,000 of those were lost to scurvy. Quite a lot. Before this time, there was this Scottish scientist called James Lind, and he conducted what's considered to be possibly the first ever controlled medical experiments. And so what he tried to do was to find out what they could do to actually stop the scurvy actually happening. He took 12 sailors and he divided them into 6 pairs, and he gave each pair something different to try. And I had no idea at this time what would actually help these sailors to actually become, resistant to scurvy. So 2 of them had cider, 2 of them were given seawater, 2 barley water, 2 vinegar, 2 oranges, 2 were given sulfuric acid. Okay, they actually had a funny thought that if they gave acid to these people that maybe that would help to kill the scurvy or something. They weren't really very sure why, but they wanted to see what would actually happen. And they studied these 12 sailors over time, and they saw what happened. Now, would anyone like to guess what was the thing that actually helped them combat scurvy? Yes. Indeed. However, he did this and he found the answer, but no one listened. He wasn't an English gentleman, he was from Scotland, and so the British Admiralty didn't really sort of consider it very serious. But however, in time, in 1794, the Admiralty gave it a go. And as it turns out, England came out on top of that war. And so we come on much further forward to modern medicine. And the medical profession obviously realised that the way to go was through controlled studies. And this is how you accomplish good medical practice. And there's an individual called David Sackett, and he's known as pioneer of evidence-based medicine. He actually really pushed, or we shouldn't really do medicine unless we have some solid evidence in order to say that it's safe and we can use it and it's effective. And there's this thing, I think some of you may have heard of something called a randomised double-blind test, double-blind trial. And that's known as the gold standard. Any drug that enters the market has to get this approval going through this double-blind test. And there's this collaboration called the Cochrane collaboration, and this contains a huge number of the results of loads of randomised controlled trials in the world. You can go there, and you can actually find all this wonderful information about all these trials and the results they did. So there's a lot of backing on it. They have lots of protocols in place. They know exactly what they're doing when it comes to applying their science. But when it comes on to things such as computer science, well, computer science goes some way towards telling you how to code software as a science. So whereas in the field, research methods and protocols to how to approach the application of science in the field, computer science only goes so far. So there's a number of realizations that you'll probably encounter in your careers when you're developing software. Developing real software well is really, really, really hard. Okay? You can know the languages, you can know the techniques, you can know the infrastructure, but often actually developing software that does a really good job and is coded well is actually not terribly easy. And so what happens is a lot of the time when it comes to practice, and I've seen this so many times in the lab, when it comes to practice, much of software development is really advocacy. So there's a guy who says, oh yes, so you're down the pub, you're having a drink with him. He's a Linux guru, knows lots about Linux, perhaps knows a lot about software development. And he says, I've discovered this wonderful thing I'm using at the moment. I hear you need to develop a website. I've discovered this thing called Kahana, say for example, a web development framework. And it's really good, it'll solve all your problems for you. But if a guy down a pub saying this is what you should do, or perhaps this guy in the lab saying this is a really good thing for you to use, where's the evidence this is actually the right thing to do? So the problem really is, what you can do is covered in computer science, teaches you an awful lot of stuff. But when it comes to actually how should you do it, and what actually is good software, there's a lot more you need to think about when you're actually applying what you've learned. However, there's lots of research that is out there that helps us to understand the kind of thing that we should be doing. There was a study done in 1975 that's been backed up by a number of studies since. And this was written by Barry Boehm. Some experience with automated aids to design large-scale reliable software. He published it. And he came to the conclusion after studying some software development projects that most errors are introduced in requirements analysis and design. And so when you're actually thinking about the requirements for a project, a good idea is to really make sure you understand those requirements. When the customer is saying to you, this is the kind of thing we want, is it really what they're after? If you really pin down what those requirements are, have a really good solid understanding, this can actually really, really help you, because correcting those errors later on can be very expensive. And so one of the things you observe is the later an error is detected, the more costly it is to address. So for example, if it takes an hour to fix something in a design of software, 1 hour, when you've actually written the code and you discover this error, it can take you up to 10 hours to fix that problem actually in the code, depending on the software. And then when the code goes live, and perhaps it's a live service, and it's in production, it's being used, and you realise this bug needs to be fixed, it could take up to 100 hours to fix. So one thing to really understand, especially in your group projects, is to really understand the requirements, what it is you're trying to do, and how you're going to do it. There's something else that was a result that was found that's been repeated a number of times. And that is the reading code, getting others to read your code can really, really help you. Okay? So there was this paper written by Fagan in 1975, designing code inspections to reduce errors in program development. And he detected this, he observed this result, that rigorous code inspection, getting others to look at your code, can remove between 60 and 90% of errors before the first test is run, even before you've begun testing. So if you're writing a critical piece of code, perhaps it's a part that does some integration with lots of other pieces of code that your colleagues are writing. Just getting them to have a look at that piece of code can really help you to find bugs in it before you even run it. And it helps to disseminate the understanding of how the code works to others in your team. That could be critical. When you're thinking about how to take the Python side of the code running on the server in your group projects, and you've got the JavaScript running, you need to make sure that interface is actually working correctly. Perhaps actually, going through some of the more critical parts of the code with your colleagues can actually really help you there. And there was this result found by Cohen in 2006. This has been found a number of times since. The best kept secrets of peer code review, and he said the first review and the hour matter most. So if you can get just one other person to look at your code, just for an hour, just so you talk through the code, and then you help them to understand how it works from your perspective. Just that process of doing that can help you to find bugs in your code. But beyond that, you kind of tend to get some diminishing returns. So actually doing that just about 1 hour with one other person can help. And there's something else as well in regards to errors. There's a couple of studies that were done of software where errors are found. They found that half the errors are found in only 15% of the modules. It may not be too hard to realise why. A lot of the time, a lot of code is quite straightforward. A lot of time when you're writing code, a lot of it's kind of straightforward. It could be setting up things, actually getting the code ready to actually run a critical part of the code. And it could be that, in terms of complexity, there's only a few modules that actually do a lot of the actual processing that you're actually wanting to do. One of the outcomes of that is if you ever find an error in your code, in one module, perhaps the thing to do there is just to keep looking. You might well find a lot more errors in your code there. There's also an issue with complexity too. So when it comes to looking at when it comes to actually thinking about the problem you're actually trying to solve and what you're actually writing in terms of code, something that was found by Woodfield in '79 is that for every 20% increase in problem complexity, there's a 100% increase in solution complexity. So one of the outcomes of that, perhaps, is to think about not making your solution too complex, actually thinking about keeping it as simple as possible. It's very easy to write complicated code. It's actually really hard to write simple code, especially in trying to accomplish something quite complex. And so when you're thinking about the problem and you're thinking about the requirements of it, there was something that was found by another individual called Gimuchen in 1991. The two biggest causes of project failure are poor estimation and unstable requirements. So when you're thinking about your group projects, make sure you get your requirements down absolutely set so everyone really understands what it is that needs to be accomplished. And this one I've observed many times. So development teams do not benefit from existing experience. They tend to repeat the same mistakes over and over again. So you might well find this when you go into industry or even academia, that when you're developing software for the first time, you'll make some mistakes, the way you do it, the way you develop it code. But actually when it comes to actually doing another project with the same individuals, often a lot of those lessons aren't actually learned, and the same mistakes are done again and again and again. A good example of that is when it comes to doing things such as testing. So often there's a real push to get code live and working, and develop features, but actually looking at the quality of the code and actually making sure that the code itself is stable and reliable often tend to take short shrift. And when it comes to testing code, often a lot of time in projects is not enough time is spent in projects actually testing it to make sure it's actually doing what it should be doing. So, I don't know about you, but when I first started programming, I just learned on my own, really. I learned in using Acorn Electron, started learning with 7, and I learned a lot about what I needed to do with languages and all this kind of stuff, just basically by learning myself, teaching myself. And as I grew up, I kept on learning more and more about how different languages, how to write code, and really, I was just kind of just learning on my own. And so, one of the pieces of advice that's generally given is, if you're going to think about writing a piece of code, why not go out and actually think about reading other pieces of code that are being written? For example, you don't just go out and write a novel such as War and Peace. You go out and read other skilled writers first, for example, before you actually see how to write a piece, how to write a book. The same is with languages. When you don't go out and write foreign language when you're learning a foreign language, you learn to read it first before you start actually writing in that language. And there was this thing that was said by Bill Gates, and you can take this or leave it, depending on how you feel about Bill Gates, of course. But something that he said that was quoted by Susan Landers in 1986 was, he said, the best way to prepare to be a programmer is to write programs. Of course, you must keep on writing, keep on practicing. But you can also study great programs that other people have written. And just to show the problem of this, in terms of what actually is good code, Carnegie Mellon in the States tried to collect examples of good code, what actually was good code, so they could show the community, the software development community, good examples of code, how it's supposed to be written. They gave up, basically because software engineers couldn't decide on what was easy to read in terms of code. They found that too difficult. And so what we're going to do today, so those are just some things you can take into consideration when you're doing a group project, and also when you go into your career. But we're going to do an exercise today called What Makes Good Code Good. It's something we've done with a number of different institutions and researchers nationwide. And we found that it can really help groups to understand what it is that actually makes code good. So when it comes to actually writing code, they can consider all of these things around writing code they should be taken into account. And so what we're doing is, well, the aims of what we'll be doing will be to help you sort of develop an understanding of what good code is. And then importantly, as we said, to start a discussion on what practices to think about in a group project, what kind of code development practices you should think about. So, throughout the day, or at the 12 o'clock lecture, so we won't be meeting here, we will meet back at 2, but perhaps at the lecture slot at 12, within a group or perhaps on your own, you could be in your assigned groups if you wish to be. Think about properties of good code. What actually is good code? Okay? Consider things such as what does good actually mean? What kinds of things make code good? You can think about things such as the approaches you take to write code, the techniques, the practices, the infrastructure you might use, tools you might use as well to actually help you write good code. And there's this form here, which I've put up. I'll show you what that looks like. It's really very simple. There we go. So I've put this on the notes wiki. And so when you're actually thinking about what makes good code good, you can go to this form, and when you have a list of these things that you think make code good, put them in to this form and just submit the form. What we'll do at the end of the day, at 2 o'clock this afternoon, you'll have a look at what you've come up with and see what you think and what makes good code good. So for example, one thing you might want to consider is making code readable. That's one thing. And another one might be commenting your code. The important reason for this is you're writing the code now, but it could be that someone else needs to read the code later to understand what it is you've done. And if you're writing code for some other project, it could be that 6 months down the line when you've written your code, you need to understand what it is you've done yourself. And that's actually quite easy to forget why it is you did something when you're writing code. I don't know about you, but I've written so many programs, and I've gone back and I've actually read them and gone, what was I thinking when I wrote that? And I've realised through a lot of hard work that thinking the why in the code, the why I'm doing something, not just the what of what I'm doing, is actually really, really important. It could be that I was coding it in a certain way to avoid a known bug in a library, but often I didn't actually write why I was doing that. So these things can really help. So that's the exercise. So what we'll do is you can find all of this on the notes wiki, and I'll send out an email directly after this lecture with the instructions again and a link to the form. You can go away and have a think about that and let me know what you think. And we'll come back at 2 and see what you've come up with. And I think that's it. So okay, thanks very much, and good luck with that exercise. I'm really looking forward to see what you come up with. Okay, so we'll close early today. Thanks everyone.
我还看你是文字什么的。啊？看你是录音。谢谢。